the last video, we talked about ring strain again, and how cyclohexane is very special because it doesn't have ring strain. But, and I drew it out here a moment ago so I could just copy and paste it before we hit go on the video, this is what it really looks like in 3D. It's kind of a zigzaggy hexagon. Now if I look at it from straight above, if I look at it, got the wrong color out, if I look at it from straight above, like in the middle like this, and I look in all directions, I'm going to see this general shape. But this doesn't really tell you that it's not two-dimensional. This does. And what I'm going to do is I'm going to place the hydrogens on it. Now, every one of these carbons, let's do this guy here. Every one of these carbons has 2 bonds to go around the cycle. That means it's going to have 2 hydrogens. And what's really important is to look at how the hydrogens are configured on here. So every other one is going to go axially up and down like this. So I can do this here. I can go up this way, down on this one, up on this one. Why can't I draw a vertical line? There we go. This one, and then this one kind of behind like that. So there's one set of hydrogens, and now the other set, maybe I'll do it in orange. They are equatorial. So this one maybe goes this way. Equatorial meaning like in the plane of the general average plane of the molecule. This one goes out this way. This guy kind of looks like comes out toward us almost perfectly. This guy is going to be out this way, this out this way, and then this guy out that way. Okay, so there's our cyclohexane. Now if I look at it from above, maybe we can just move this out of the way a little bit. Let's do that. Let's move this out of the way. Okay, that's out of the way. If I look at this from above, it wouldn't exactly look that way because these equatorial hydrogens are going to be straight out like this, every one of them. And then what did we use for, is that the same yellow? I think we used this gold. Now the axial hydrogens, these ones that go straight up and down, are just going to look like dots here like this. And you only see every other one because you're looking from above. You see these 3 that are up here. Ones that are beneath, maybe I'll do like a dotted circle like that, would be pointed straight down. So you can't really see them from this exact angle of the molecule. But this is how the hydrogens are arranged on cyclohexane. And I think from the 2 diagrams you can probably see what I'm trying to say here. Okay, now I'm going to take that exact same conformation of cyclohexane. But what I'm going to do is I'm going to adjust the orientation of these hydrogens. I'm going to rotate this guy up, I'm going to rotate this guy up, and these guys will flip down. So let's see what that looks like. I'm going to have this be our vertical this time, up instead of down. This one will come down, this one up. You get the idea. You're with me on this. This guy down. And so what does that make our equatorials? Well, those are going to look the same. Like that. H is all around. H is all around. Now, why does this matter? Well, believe it or not, these are slightly different. Now that I've got them drawn, let's make the point that I'm looking for. So let's look at this bent up carbon here. This is the highest point on the molecule. Well, the closest 2 carbons to it, here and here, their axial hydrogens are pointed down. So the distance here is pretty high from one that's bent up to these hydrogens that are pointed down. So that's cool. When I look at it on the other side, this one that's bent up, those same hydrogens are up here now. And that's actually quite a bit closer to this bent up carbon. So these positions are different. They're not identical by any means. Now the thing about it is these 2 types, axial and equatorial, can convert between each other. We call it a ring flip or an interconversion. And you can ring flip readily. Even if I have, where's my orange at? Let's say I make this a methyl group here. I put a big giant carbon constituent on here like that. So I got a big heavy mass on this corner or something, carbon heavier than a hydrogen, right? I can still interconvert. I can fold this down, take this hydrogen with, and the whole ring will all adjust. These will flip up, these will flip down, everybody will switch like that. And what you do is you end up with your CH3 down here, like that, and you end up with your hydrogen over equatorially like this. That's a ring flip. And this interconversion happens all the time, at least at room temperature. This happens readily. It happens without any kind of influence necessary. It just happens. So you can think of this as methyl cyclohexane because there's one methyl group on your cyclohexane, but it also does it with bromocyclohexane or hydroxycyclohexane if you put an alcohol on it or whatever functional group you're sticking on. Your hexane ring can still convert these positions. That's not going to be in between. It's not free-floating. This is a geometry of a tetrahedron here. But it can flip like a light switch. Click, 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 up, down, up, down. It can absolutely do that depending on what the situation is. I want to make it really clear. Take some of these arrows away. I'll just keep this methyl cyclohexane like this. This is the more stable of the two conformations. This methyl group is farther away from everybody. If I put it here, CH3 here, he's much closer to the neighbors than this hydrogen out here is right now. So these aren't the same, and it does switch readily between them, but this is the more stable configuration. Okay, so let's put that methyl here to match, and we'll have it be that this equatorial methyl cyclohexane is going to fold down, take this hydrogen with it, and everyone's going to rotate to accommodate. That's a nice little wrap right there, rotate to accommodate, and we'll create this situation here. This methyl group is too close to these hydrogens, three-dimensionally, right? They're all hanging low. So they're kind of close to the same plane. And this is too close together. It's not ideal. This guy out here is out in his own world. He's not interfering with anyone like this. So that is why axial methyl cyclohexane is a little bit sterically hindered. Steric interference you can think of as these crowding each other's personal space. And stay out of my personal space. Remember, CH3 isn't just something pointed down here. There's going to be like 3 hydrogens sticking off of it in these directions. So there's a carbon here, and these hydrogens here, well, they're encroaching. This is definitely not ideal. But the methyl group, well, I'll leave that one there. This methyl group, his hydrogens are like coming out this way. They're not bothering anybody. You see? Let's take all the hydrogens away and put a couple of methyl groups in here. And we'll call it a dimethylcyclohexane. Our names are starting to get pretty cool. That's how you know that we're really smart, is where we have names like dimethylcyclohexane. So let's put one, we'll call it equatorially here, CH3. And let's do one axially. I'll stay with the convention here like this. Axial CH3, like that. And of course, as you know, there will be hydrogens like this. Every other carbon will have one pointed up, like so. I want to do a Newman projection right down this bond angle here, this bond between the two methyl groups, okay? So here's my circle. Let me get the yellow out. Here's my axial CH3. And then my equatorial CH3 is still above flat. Still on the same side of the plane. If I was to draw a total flatness here, it's still above that. We call that a gauche interaction. Where'd that 3 go? Come back. There. This is a gauche interaction. They're too close. It's spelled gauche, like that. It's a French word, I think, but I just think of it as an interaction between the two methyl groups. But you also want to notice that there's interaction between these hydrogens here. That methyl group is encroaching. Remember, that's a carbon with his 3 hydrogens kind of coming out this way. These hydrogens are going to be a little bit too close to these hydrogens here for there to be total happiness. So what we're going to say is we have 1 gauche interaction and 2 methyl hydro steric interactions. Steric is spelled like this in case you've never seen it. Steric. Okay, we'll call it a diaxial interaction because it's 2 axial groups interacting with each other, trying to crowd for space. The theater is a little too full. Now, as we're talking terms, I might as well add this in. This is the cis dimethylcyclohexane because these two are on the same side of this flat plane here. Now let's take a look at trans dimethylcyclohexane. All I need to do for that, I guess we could keep this axial methyl group here, and we'll make the other methyl group, oh, we could put it down here. We could do that. And of course the hydrogens are all there, but let's do our Newman projection. You're going to have 1 CH3 up this way and 1 CH3 down this way. That is what makes it trans dimethylcyclohexane. Cyclohexane. You get what I'm saying. So just keep that in mind. There are 2 different types of dimethylcyclohexane. This is 1,2 because it's on carbons 1 and 2. It doesn't matter which one you label 1 or 2 in this situation. But guess what? These being far apart are going to be much more favored in terms of this steric hindrance here. This methyl group is encroaching on this methyl group. They're going to fight for space. But over here on opposite sides of the molecule, this guy doesn't even notice this guy down here. So it's really important to kind of think about cis and trans configurations and conformations. But typically trans is going to be better. It's going to be lower energy because these are so far apart that they're not so sterically hindered. So this kind of conformational analysis takes a lot of practice. I'm not very good at it, but we're getting through it together. So we could replace these with all kinds of things and take a look at the energy involved if you look at the individual interactions at once. So don't just try to do the whole molecule at once. It doesn't really work that way. To watch this full playlist in order, click on the video here on the left, or to go to the next video, just click on the video here on the right.